Yeah.
Yeah, what's up with showing up 4 out of 5 hours?
Yeah. Yeah.
We should start it out really well.
Okay. Hi, everyone, and welcome to the final lecture of our senior project. Okay, so we're going to talk about some actual applications of quantum mechanics, which is cool because when you first look at quantum mechanics, it can look a lot like just math. Okay, so this is a reminder of entanglement. And so what we've seen before, what entangled states are, is when the outcome of one particle is dependent on the outcome of another particle. So in this state, we can't have particles with both spin up or both spin down. Do you guys see that? Do you remember the notation? You see how like it's a half probability that one spin up and one spin down, and half probability is vice versa. But we're wondering, are there any other states, entangled states, and like how do we come up with forms for entangled states? Okay, so we're going to look at the difference between classical mechanics and quantum mechanics. So in classical mechanics, we can keep track of the position and momentum of every single particle, but we can't do the same in quantum mechanics because of the uncertainty, right? We can't do everything at the same time. Okay, so here we have a setup where we have one particle and another particle, and they are both indistinguishable. And so we're going to have them collide in the center. If you know everything, do you know what hole they're going to end up in? I know. An answer. Do you guys know which hole they're going to end up in? You know what I mean? Right? Classical mechanics.
Is particle 1 in the top left hole?
Yes. Yeah. I mean, theoretically, it could be the other way too, but it depends on what we know. This collision, we can predict exactly the results, which is awesome, and we think we know everything, and we think we're really smart, but it turns out the world is not that way. Okay, so here we're going to write down the state for it if we're talking about classical mechanics, where we can just say A goes in hole 1 and B goes in hole 2. There's no probability here. We know it. We're really smart.
Particle 1 and particle 2, not...
What did I say?
You said...
Did I flip it? Yeah, particle 1 goes in hole A and particle 2 goes in hole B. Yes. Okay, so in quantum mechanics, the same is not true, which you might be able to guess. So what would happen is, like, if we're looking at a quantum state, we would see the outcomes. We'd say that one particle is in hole 1 and the other is in hole B. Sorry, wait. One particle is in hole A and the other is in hole B. This is really difficult. Okay, I got it. Hole A, particle 1. Okay, so we see that one particle is in hole A and the other is in hole B, but do we know which particle got there? Which particle got in hole A? We don't know for sure, right? If it's if we're looking in a quantum mechanical system, we don't know the position and momentum, right? At all times, we can't know both. So we can't really trace it back anymore. So we have this end solution and we don't know exactly how we got there. And we realize we're not all knowing, and then we feel sad. But it turns out, yeah, so both of those are possibilities. So we do know at least the quantum state, right? So here we have the state where particle 1 went in hole A, and particle 2 went in hole B. I got it right that time. And particle 1 went in hole B, and particle 2 went in hole A. That's the generic state, see there? And we have coefficients. And the coefficients are related to the probability of that happening, right? And then we have the swap state where the two probabilities are swapped that happens. And because the particles are indistinguishable, we know that we can set the generic state in general equal to a constant times the swap state where the constant has magnitude 1. And at first I was like, well, magnitude 1, why didn't we just write 1? But of course, what has magnitude 1 besides 1? E2. Well, yeah, but also, yeah, exactly. There are lots of different things. Okay, so now we're going to do a little bit of math. Very exciting. Okay, so we're going to set the two states actually equal to each other. And when we solve it, is that this constant times alpha must equal beta, and this constant times beta must equal alpha. So we can know that the constant is plus or minus 1. So not imaginary numbers, but like actually 1 or -1, which is nice because, I don't know, I prefer real numbers to imaginary. I have that bias. Okay, so yeah, we have these relationships between the two. Okay, so what we're going to call this is the state where we set it equal to positive. We're going to say that's the symmetric state. And the state where we let k be negative is the anti-symmetric state. Okay, so, yeah. So quantum mechanics says that two identical particles can have only these two kinds of states. And yeah, and so when we're looking at states, they're either symmetric or anti-symmetric, which is determining whether it's positive or negative. Okay. So,
Why are they symmetric again?
What?
Can you show me why the state is symmetric or anti-symmetric?
You mean like,
Like just by looking at the expression of the states, how do you see symmetry or anti-symmetry in these states?
oh, like, you mean like the fact that in the symmetric state, the probability of either thing happening is the same?
Well, that's also true in the anti-symmetric state, right? In the symmetric state, state AB has a 1/2 chance, and state BA has a 1/2 chance. And same thing in the anti-symmetric states.
So wait, wouldn't that come up with the next question that's on here?
Right, but I still don't see where the symmetry comes from.
Wait, I don't know what you're looking for.
So symmetry, what symmetry really means is when you switch the indexing of particle 1 and 2, if it's symmetric, that means after the switch you get the exact same state. If it's anti-symmetric, it means if you switch the index, you get the negative of the original state.
Oh, okay, that's good. Yeah.
Right? And so in the symmetric case, if you swap the position of AB everywhere, instead of AB plus BA times 1/√2, you would get BA plus AB, which is the same as the original thing. But if we swap the AB in the second one, you would get BA minus AB, which is the negative of the original.
Yeah.
So that's what symmetric and anti-symmetric means.
Yeah, and the probability of both happening is the same in both of them because you'd square it. So, okay, that makes sense. Thank you for clarifying, guys. Okay, so there is also an experimental way that we can distinguish between the two. Okay, so let's see, does it reveal the answer? The answer will be different. Okay, let's say that instead of having two holes, A and B, we instead had one hole, and we tried to shoot the two particles into that one hole. So how would we write the states? Instead of AB, let's call this like third hole C, because we're creative. So how would we write that in this notation? We want both of the particles to go into hole C. So I could just,
Like double C, right? CC.
yeah, right? Does that make sense? So we have particle 1 going into hole C, particle 2 going into hole C. So the way we can tell the difference is that possible if we're in an anti-symmetric state? The answer is no. Because if you plug in CC, the negative will cause the two to cancel out. So we have a 0 probability of that happening if we're in an anti-symmetric state. So this leads in, so yeah, it's impossible to have them if they're in an anti-symmetric state and both end up in hole C. This leads to the Pauli Exclusion Principle. How many of you guys have heard of the Pauli Exclusion Principle? In chemistry, perhaps? Physics? Life? I don't know. Your free time? So what the Pauli Exclusion Principle says is that two identical particles that conform to anti-symmetry cannot occupy the same quantum state. And so what we were showing earlier were quantum states. So yeah, the easiest application of this, which you might have seen before, is to the atomic structure. Okay, so at one point we thought that, and in middle school this was actually how they taught it to me, that electrons just orbit around the nucleus, like planets. Very cute, very easy for middle schoolers to understand. But unfortunately that is not true. So in quantum mechanics we know that electrons have 4 different properties, which is energy, angular momentum, the latitude of the electron, and spin. So this describes energy. Do you guys see how that would describe energy? Would a particle that is closer in or further away have more energy in a closer orbit?
And assuming that the electron has negative charge and the nucleus has
True.
positive
True,
charge.
yeah.
You have less energy than the lower orbit.
Wouldn't it be more than the lower orbit? There it is.
There's less energy in the lower orbit,
Oh,
right?
whoops, never
I
mind.
think. Wait a minute.
Yes. Yeah, yeah, that, yes. So, but yeah, so exactly, the location on the, on this model will show us how much energy this electron has, but it won't tell us about the other promoters. Okay, so angular momentum, you guys might be familiar with this, is mass times velocity times radius, are good terms. And quantum mechanics tells us through something that is a little too complex to drive, that angular momentum is quantized. Have any of you guys heard that before? Angular momentum is quantized. So what that means is that we can't have like an even distribution of angular momentum. Like you can't just say, oh, I would like an angular momentum of 2, and that might not be possible. We only have these set values, 0 h bar, 2 h bar, minus h bar. And that's all that nature allows us to have for the electron's momentum, which is what it means by quantized.
Well, that's actually, those are the allowable ones given a certain energy. If you have a
Yeah.
higher energy, then you
Right.
can allow more. But they always come in discrete intervals.
Yeah.
So they're separated by h bar.
Yeah. So as you go higher up, there will be more options. Okay, so we might think that, yeah, if we fix L, we can still change V and R because those are components of L. So, you know, you could have a higher velocity but a lower radius, and that would work. But what's interesting is that the latitude is also quantized. So what you can see here is that these are the kind of paths. What's a good word? What's the paths that the electrons are taking here in this visual, and that the latitude would be like how high up we are. So the electron could be traveling here, or here, or here, or here. You guys see the different circles? Yeah. So that would be the latitude, and those are only available in quantum intervals. So I can't be here as an electron. That's like a forbidden zone. Just here, just here. That's sad life. I'm fine.
So because the intuition for latitude is just literally if you put a spherical shell around the center of this coordinate system, then think about you living on Earth, then you would have higher latitude, basically means closer to the North Pole, and then latitude goes down like that. And then what Lydia is showing you is that those come in quantized levels, so you cannot be anywhere on Earth, you can only be in some spots.
And it is right to say that the origin would be, in this example, would be like the nucleus, more or less, right? There it is?
Don't keep asking me.
Okay. The origin is the nucleus. I'm saying with confidence this time. Okay, so then we also have spin. And so here's a kind of rough visual here to imagine it, is that the electrons are more or less rotating, and they can rotate in either direction. And so again, obviously this is a visual, but you can see that an electron rotating this way is different than one that's rotating that way. Well, that would have to do with the velocity in the angular momentum. Or no, wait,
Actually, that's a good question, right? Because if you see on the graph, I only have plus 1/2 and minus 1/2. So it turns out what's interesting about the quantity spin and how it's different from a classical angular momentum. Think about it. If you just have planets rotating around the sun, and each planet is rotating about its own axis, the rotational velocity of each planet around its own axis can change, right? You can make it faster, you can make it slower. But in the case of electron, that's why Lydia said that the classical analogy breaks down, because the spin of electron can really only be plus 1/2 or minus 1/2. So it's not really the same as classical spin. But this is just a model for you to see two different orientations. But there are only actually one possible value for the magnitude, to answer Isaac's question.
Okay. So what the Pauli Exclusion Principle says here is that an electron, so we characterize it by these four properties, right? Is that you can't have an electron that are, two electrons that are in the same state. You guys might have seen this in chemistry before when you're writing out those long states of electrons. Is that you can't have one where they're in the same orbital and they have the same momentum, same latitude, and that their spin is also the same. And what's interesting is that, do you guys remember, can we measure momentum and position at the same time? No. But we can measure all of these four things at the same time, which is nice. So we can measure all four of these at the same time, and if they are all the same for, well, they can't be all the same for two electrons. We'll find that when we measure them for electrons, we get different combinations of these four properties for all of them. Yeah, so for example, for a given energy, angular momentum, and latitude, there can only be two electrons, one will spin up and one will spin down. So this helps us generate our favorite table, the periodic table. With different bond numbers on here. Okay, Jerry, do you want to? Are we taking a break for problems or?
No. Wait. Are you not talking about the periodic table?
I don't like it. I lied. It's not my favorite table.
Okay. I guess I will come.
I do have a question.
What's your question?
Why is it not a violation, go back a slide,
Yeah.
of the Pauli exclusion principle to have two electrons in different atoms with the same E element?
Well, wouldn't that just be because they're like, those would be within separate quantum states, right? Or not separate, wait, separate systems entirely. Right?
So can electrons in a molecule have the same
No.
element? So what defines a separate system as opposed to a
Well, because the position, wait, wouldn't it be that, that within those, it would be that they would be, that latitude would be defined relative to that origin, right, which is the nucleus. So if you're in a separate, atom, you have a different origin. So you're like transitioning over. So they wouldn't be at the same latitude. I don't know if that's the right.
Well, yeah, or more fundamentally, it's just that the interaction picture between your electron with this nucleus is different from that electron with the other nucleus. And so if you take one electron here and another electron here, this electron energy and momentum stuff, they're all sort of defined by the potential energy that's created by the nucleus, because they're interacting through the Coulomb force. But if the other electron is far away, and we assume that there's no interaction between the two systems, or the force is too small to affect each other, then this electron state is independent of this electron.
So it's not why we need to. So if it were the other way around, then could assume that that you can only occupy one space in one state and an entire molecule, then you would need to have like lots of like a particular
Right, and in a particular molecule, in a particular interaction between, say, so, and another thing that's important is because in the periodic table, you take the nucleus, or take a number of protons, and you fill electrons to different orbitals. So electrons can fill up more and more different states as you increase the energy that you allow. So basically what happens is that if you have multiple electrons in orbital, you assume that the electrons don't interact with each other, because that interaction is much weaker than the interaction between electron and the proton, or proton and the nucleus. So then you just basically look at each electron independently, and all their states are described relative to the nucleus. So then they cannot occupy the same state.
So in a metal that has electrons that are conducted potentially, are those electrons each in a unique state, or are they able to share similar states?
Well, that also depends on how the electrons interact with each other. So sometimes electrons can actually pair up. So the electrons are bound together in a sense, and then a pair of electrons act together. And that becomes different from, so those pairs of electrons can actually occupy the same state. whereas the electron inside a particular pair cannot, because they're actually interacting with each other, whereas the two pairs, they're not interacting independently. So it really, the definition of all these properties are all based on a particular force that's mediating the different particles. So it matters what kind of interaction. And to actually look at the details is going to become a lot more difficult, a lot more messy. So it's remarkable that this Pauli Exclusion Principle gives us correct predictions for the periodic table. So, okay. Do you have something more to say about the periodic table?
No, I'm not.
Yeah. But basically, you can see that as n increases, n, the principal quantum number is the label for energy. So as n becomes bigger, the total energy becomes bigger. So as there's more energy, you can fill more electrons into around the nucleus, and you have a lot of them in the nucleus. Yep.
Why do certain elements, why do certain columns have to have a certain spin?
Oh, that's just the way you organize it.
Okay.
It's the way you organize it so that, so basically the spin is actually pictured as, so plus 1/2 spin is boated. So spin is all the boat. I'm not sure if you guys can see this clearly. But like, for example, this entire column is boat, the second column is not boat, and then the first 5 columns here are boat, and the next 5 columns are not boat. So you can see that the 5x5 square here is actually exactly identical as the 5x5 square there, except that all of these are boated because that's the spin in one direction, and that's the other 5x5 square is spin in another direction.
You'll learn in chemistry that the electrons fill these orbitals one at a time prior to pairing up, in order to reach the minimum energy state. So they can all have similar spins as they go across, but if you look at those 5x5 blocks, once they start to fill in pairs, well then, as they just told us, they must have opposite spins. Otherwise, they'd have the same quantum numbers.
And you notice that the value, and once you set the value of n, you basically you constrain the range of value that the angular momentum L and the latitude m can take. So, they're sort of related quantities, but each of them have quantized values, so we can have sort of discrete combinations of these values. Okay, so again, going back to the symmetric and antisymmetric states that Lydia talked about, we can say that what's interesting is, in the atomic orbital example, all the electrons are always living in the antisymmetric state, which means this property is something intrinsic in each type of particle. It's not that, the electron can sometimes be antisymmetric, sometimes be symmetric based on circumstances. It turns out that particles are always in antisymmetric state or in symmetric state. So that gives us a way to characterize particles. And these two classes of particles are called bosons and fermions. Have you guys heard of these terms before? Somewhat? Thank you, Eric. So, what are bosons?
Bosons are particles that are described by the symmetric case, aren't they? Where you add to infinity.
Exactly.
Or where you subtract.
Great. What other properties do they have?
Beyond that?
Yeah.
Well, you can describe bosons as force-carrying particles and fermions.
Force-carrying particles. Why do we need some particle to carry forces? Isn't force just like, something that mediates the interaction between two particles? Why do we need another particle to carry the force?
I actually don't know that.
Me neither. But that's an important question that's yet to be solved in particle physics. Actually, that's not true. Some of them are solved, but it's unclear how generally they can be solved. But let's look at the properties first. So, particles that always live in the symmetric state are called bosons, as Eric said. And bosons always have integer spin. So what was the spin of an electron again? Do you guys remember? 1/2. So electron is not a boson. So what are bosons? Bosons are force-carrying particles. We'll explain what that means later. And then an antisymmetric state, we have fermions. And fermions have half integer spin. So is electron a fermion? Yes, electron is a fermion. How about 2 electrons paired together? It's a boson. Excellent. So if you have 2 electrons, intuitively you think about it, if you add up the spin, it can either be 1/2 minus 1/2, which gives you 0, or 1/2 plus 1/2, which gives you 1. So a pair of electrons, in sort of intuitively, non-rigorously, you would get either 0 or 1, which is an integer spin. So Michael is exactly right. If 2 electrons are paired together, they actually behave like bosons. It's a very strange phenomenon.
Just one minor correction, would it be 1, 0, or negative?
It cannot be. Okay, yes, you're right. Thank you, Eric.
Wait, have you paired these? How are you pairing the electrons?
So the way you pair the electrons is, so usually 2 electrons would attract each other. Oh, sorry. They would repel each other, right? But in special circumstances, if you think about metals filled with, say, positive ions, then you would have 2 electrons in which one of the electrons actually attracts some of the other positive ions. And then, wait, is this picture correct? I'm actually not sure about this. So, okay, I might need to draw a diagram or something. So you have an electron here, and an electron here, right? And you have some positive ions filling in the middle. So electrons, if they attract the positive ions in this direction, then the positive ions will in turn also attract this electron here. So it will provide an attractive force between the electrons, so that they're in some ways bound together. And this kind of bounding this is really a quantum mechanical phenomenon, but this is a very, very crude classical explanation. But this appears as what we call Cooper pairs. And these Cooper pairs behave, pairwise, they behave like bosons. And they can be in the same state when described as a composite object. And in fact, if you put more fermions together, 2 fermions can give you a boson. How about 3 fermions? Fermions. If you add up 3 things with half integer spin, you will get something with half integer spin. And 4, you will get bosons. So basically, even number of fermions would give you a boson, and odd number of fermions would give you a fermion.
The properties with a pair of 3 electrons have been stated that this 1 electron.
I actually don't know if you can pair 3 electrons together. Do you know anything about this? I'm not sure.
So, unless you're imagining some sort of nuclear process where you have a fundamental particle which gains 3 electrons worth of fundamental particles, but then potentially
I don't think you can pair 3 electrons together, but you can definitely, like tritium, is that what it's called? 3 isotope 3 hydrogen. You can definitely pair 3 fermions together. And I think what happens is that if you look at it, if you look at it on a macro scale, it functions identically. Its spin statistics is identical to just 1 fermion, but there's a very small amplitude of it exchanging 1 or 2. But the amplitude is small enough that it's usually just referred to as just a 1 single acting unit fermion.
Yeah, so basically the idea is that if you have 2 blocks, as Eric talked about, the individual ones between the 2 blocks don't just randomly exchange with position to each other. If they do exchange amplitude, it has to be the entire thing. So when they make collision, you cannot have just 1 fermion in here jumping to the other side, but you have to have the entire thing jumping, because that's just an ambiguity in the end trajectory. If you have a part of like conglomerate particle 1 going to A and 2 going to B versus 1 going to B and 2 going to A, those are the only 2 possibilities. You cannot have part of 1 going to A and part of 1 going to B.
But I want to say, though, I'm trying to remember if Berman said that at a high enough energy, that kind of breaks down a bit. I feel like they might start.
Yeah.
So I think at a high energy, they don't.
At a high energy, they're no longer paired in the same way.
Right, yeah.
So you have to, bound them very tightly together in order for this to work. And also, these are really just weak field approximations. So as Eric said, in the stronger field, everything, the simplistic picture here really breaks down. So, So yeah, all the fermions are what we call matter particles. So they compose, us, our everyday life, the chair, the ground. And bosons are force-carrying particles. How do we understand bosons as force-carrying particles? Easiest way to do it is to imagine a snowball fight. So if bosons are snowballs, and suppose Eric and Lydia are having a snowball fight, notice that they seem to, these are not pictures from winter, unfortunately. Cannot find the pictures from winter. But if they're doing a snowball fight, what happens if two of them are running toward each other, and then one of them throws a snowball at the other one, and the other one catches it? Assuming there's no friction on their feet. So they're sort of like on an ice rink, maybe, and they're just gliding past each other and then throw the snowball. So here is, for some of you who went to physics club, this might be familiar. So what happens is they will travel near each other, then Lydia pulls out a snowball, passes it to Eric. So when Lydia passes the snowball to Eric, what happens to Lydia? The snowball is passed in this direction, in the opposite. Yeah. So originally her velocity is going just to the left, right? But when she passes the snowball, it curves down, right? So Lydia's trajectory curves down like that. How about Eric? When he catches the snowball, it goes up. The trajectory has to curve up, right? Eric would curve up. So what really happened? Can you tell the difference between this and just two electrons approaching and exerting force on each other and scattering away like this?
Bosons carry any attractive force?
Good question. That's where the model breaks down.
Okay.
Yeah. In some ways, I don't know if this is, I cannot say this for sure, but in some ways, maybe you can pass things with negative energy in quantum mechanics, in quantum field theory, for which this might work.
So we pass a negative, that's so.
Yeah, okay, but I'm not sure. Don't quote me on that. But this model really only.
Is there no way to draw a Feynman diagram for
There is a way to draw.
attractive?
You can draw a Feynman diagram, of course.
For attractive forces?
Yes, of course.
Oh, okay.
This is essentially the idea behind a Feynman diagram, but it's very crude because you're talking about snowballs. And also, where does the energy come from? How can Lydia suddenly just pull out a snowball and then throw it, and then Eric catches it, and then suddenly the snowball disappears? That's related to something called the energy-time uncertainty principle, but we won't get into that too much. We don't have time. But you guys can look it up later. Sick. So yeah, in the standard model of particle physics, you have those 6 different kind of quarks and 6 leptons, and here you have is it electron, neutrino, muon. You can't read all of this, but just all the 12 particles here are called fermions because they're what we think composed of ordinary matter. But the 4 particles here are bosons. Why do you know they're bosons? These characterize their spin values. Spin 1, spin 1, spin 1, spin 1. Whereas here you have spin 1/2 for all of these.
Wait, why is there's 2 pairs of negative?
That's charge.
Oh, that's right.
That's not spin. Yeah, the spin is only on that level. Yeah. So, can you guess if bosons are force-carrying particles? Can you guess the 4 bosons here, what forces do they carry? I gave it away.
Photons.
So let's start with photons. What do you think photons carry?
Electromagnetic.
Yes, electromagnetic force. Because that's where you learn what photons come from, electromagnetic waves. And in standard model of particle physics, you think about photons as the carrying particle for electromagnetic interaction. How about gluons? Strong force. They're glued together. So that's called gluons. It's very strong gluing force between these atoms.
I think that's legit.
I think,
Well,
yeah,
I think that's actually what it's
it's
called.
kind of legit. I don't know. And then the W and Z bosons are quite obvious if your eyesight is good enough to see this.
Why does the weak force
Wait.
get 2?
Huh?
Why would it get 2?
I don't know. I haven't studied standard model yet, so. But they carry the weak force.
Is the weak force an attractive force or a repulsive force?
It's attractive force. But this interesting.
Well, like the photon,
There's a,
like photons carry electromagnetic force, right?
yeah.
So does that mean they can carry attractive and repulsive electromagnetic forces?
Yeah.
That'd be my opinion.
Yeah. That'll be the case. Although, you know, when you get into the details of this, all our discussions will break down because really the analogies here, I don't think scientists have figured out a way to explain quantum field theory in a very intuitive way. It's still a highly complex mathematical theory. So here we're really just looking at the how we categorize them, and that'll be useful later. You might be wondering, where's gravity? Can we put gravity into the picture? So far, no. So you have this idea called graviton. For those of you who went to Dr. Aguirre's talk on Friday, you know that graviton is, proposed to be in the center model that it can mediate gravitational force, gravitational attraction between particles. But it turns out that there are a lot of problems with gravitons. So currently, scientists don't really know how to solve these problems. That's why the most active field of theoretical physics research is called quantum gravity. So basically incorporating gravity into the quantum physics perspective. So all these particles live in the quantum physics regime. Okay. So the important thing to take away is that quarks and leptons, what we think about as fermions and matter particles, they can never appear in the same states at the same time by Pauli Exclusion Principle. However, the force-carrying particles such as photons and gluons can appear in the same state. So in the next 2 sections, what we're going to do is we're going to look at different possibilities of putting bosons into the same state and how that can create strange types of effects, and how the fact that fermions cannot live in the same state can also lead to interesting effects, such as neutron degeneracy pressure, which supports neutrons and prevents it from collapsing. So, I talked about this, sorry. Do it in grad school, so you have to wait a couple of years. So, okay. Now, question? Huh? Not yet, after this section. So now let's begin our discussion with identical bosons. So if bosons can be put into identical states, we have 2 questions that we can ask. One is, how do we do that? How can we actually push bosons into identical states? That's a non-trivial task. The second is, what is special about the state? Why do we care about photons all congregating in the same state? So to understand the first one, we have to look at the ideal gas. So think about air in this room currently. The air is very hard to study. First of all, because air molecules are fairly small, but also because they're moving in random directions with random velocities very quickly. So if on Earth, with ordinary temperature, it's very difficult to study air molecules. But Stephen Chu, this physicist from Stanford, had a very interesting idea in the 1980s when he was looking outside of his window while he was working in his office. He saw snow. Snow in California, can you believe that? I don't think he was working in Stanford back then. So he saw snow. So why would snow be useful in this case? So in snow, you can actually see air and water coming together in those, little, I don't know how to describe them. They're not molecules, but snowflakes, maybe something like that. And then you can actually study the properties of these snowflakes, although you cannot individually study the properties of the air molecules because you cannot track them. So the idea that Stephen Chu had was that atoms in general are moving so fast, but what if we cool them down? The question really is, how do we cool them down? So he thought about, so cooling them down would be nice, but it's very difficult. And they spent about 20 years to develop different kinds of techniques for cooling down particles. Initially, they could cool down particles to about a couple millikelvin. Do you guys have an idea of the temperature scale Kelvin? So Kelvin is basically Celsius plus 273-ish. So it's like basically Celsius. So basically higher Kelvin means the environment is hotter, and lower Kelvin means lower. So a millikelvin is really, really, really cold. But that's not the coldest place in the universe yet. In the about year 2000, I think, scientists actually pushed the temperature to even lower limit. So to see how cold this place really is, you can think about the astrophysical objects that we observe around the Earth. So how hot do you think the sun is on the Kelvin scale?
Surface or in the center?
Surface. I'm actually not sure.
30,000 Kelvin.
How about the center? Okay, so but it's on the thousands scale, right? Thousands of Kelvin. Okay. So, but yeah, that's the data I got. But whatever, it's on the thousands scale, so it's pretty hot. How about the Earth?
298.
298. Okay. 298 minus 273. What's that? 20, 25 Celsius. Okay, that's about right. That's 3. Huh? 25 Celsius? We're going to convert to Fahrenheit. I can't do that. It's like 70s maybe?
9/5.
78.
That's very specific.
Yeah, so about 78 Fahrenheit. But yeah, don't worry about it. It's 300 Kelvin. How about the cosmic microwave background? That's about the temperature of, basically, if you look at just the empty universe. You have electromagnetic radiation filled in the entire universe.
2.7.
2.7. That's very precise. 3 Kelvin. So Eric was more precise. One extra significant digit.
So the core of the sun can be 15 million.
15 billion Kelvin. Yeah, so that's really hot. Well, really, we're getting to really cold. So just think about, on average, the universe has a temperature of about 3 Kelvin. So can you even imagine a millikelvin or nanokelvin? Physicists have done that. They can actually reach 20 nanokelvin in the most recent experiments done in, I think it's University of Colorado, Boulder. If you guys are familiar with it, it's very strong in atomic physics. They have a lab there that studies these ultra cold atoms.
They study, or how do they take the temperature of
Hmm?
How do they get the temperature of these?
Good question. I do not know. I do not know.
Technique.
Also, temperature is it's really hard to understand temperature at a very low level, because the way to think about temperature in classical mechanics is to think about it as, something that's sort of proportional to the energy, internal energy of the system. So if the molecules inside have a higher average velocity, has a higher average kinetic energy, so has a higher temperature. And in a quantum case, when you reach such a low level, and to the point that we'll later see, particles cannot even be distinguished from each other, how do you really characterize this idea of a temperature? So I don't really know, but I think it must be some kind of sensing device that doesn't directly measure the temperature, but measures something else and converts it to temperature. But if you guys are interested, you can look into that. Yeah, so in this model, the classical statistical mechanics model, you see that higher temperature corresponds to higher average kinetic energy per molecule. So, as we said, if I cool down a cluster of bosons, notice it's a boson. If it's fermions, this is not going to be very useful. If it's a bunch of bosons, you would expect the energies to drop. But how do we know how low the energy actually drops? So we know from quantum mechanics that there is sort of like a lower limit to the energy. Do you have a question, Anna?
Yeah, it's way back little, so there's
Yeah.
some bosons can be composed for.
It depends on your definition of bosons. If you only look at fundamental particle always are either bosons or fermions. But if you combine them into composite objects, they can exhibit properties.
Because our states-split bosons are not by the same scale on a position.
Not in the case of the force-carrying bosons. They're not made of fermions. Bosons have their independent existence. And bosons, we talked about photons, gluons, and WZ bosons. All of these, they're not made of, on a more fundamental level, they're not made of fermions. But you can compose fermions in a way that they behave as if they're bosons. And that's why the example we're showing here with cooled down bosons, that's doable for photons and gluons and stuff, but it's also doable for Cooper pairs, where you have pairs of electrons. And that's verified in 2003, I think. That's harder, much harder to talk about, because you have to deal with when does the Cooper pair actually break down? When does it stop behaving like a boson? So in order to understand what happens in this case, we're going to do a little bit of thermodynamics. Thermodynamics is basically the study of heat, how temperature, entropy, those macroscopic quantities arise from analyzing the microscopic probability distributions. So suppose that we only have two energy states. This is obviously not true in general, but suppose we only have two energy states. We have the lower state and the higher state. So the lower state is E1, the higher state is E2, and they're separated by the difference E. So in thermodynamics, there's this Bose-Einstein rule that says the probability of finding an extra particle in a higher energy state is proportional to e to the negative E minus t, E divided by t, where E is the energy difference and t is the temperature. So notice that e to the minus that is always smaller than 1, right? Do you guys agree? T is temperature. Hmm? Oh no, the two energy states are the allowable energy states. And you have n particles that will be occupying states, and depending on how they occupy the states, they have different temperature. So if I know the temperature, then I can figure out how the states are distributed. So because e to the minus e divided by t is always smaller than 1, that means there's always less of a chance of finding an extra particle in a higher energy state. Because there are less configurations there. So suppose we have n bosons, and k of them have energy E2, which is a higher energy, and n minus k of them must have energy E1, right? And that's how we describe the system. So what happens to the distribution of the particles as temperature gets lower and lower and lower?
What you have is that you'll have 1 over e to the, basically the t will go to 0, so that whole thing will go over 1 over infinity, right?
Indeed. Do you guys see Eric's argument? What he's saying is that if we cool the bosons to very low temperature, so T becomes very near 0, say 20 nanokelvin, that's very, very low, then e to the minus e divided by t would be an infinitesimal number, right? Because e over t will be infinity, will approach infinity. And then minus infinity, e to the minus infinity would give you
1 over e.
basically 0, very close to 0. So the probability of finding an extra particle in a high energy state, if it's proportional to that quantity, that's going to get really, really, really small if k becomes, if t becomes really, really small. And we know that k can, yeah?
It's just going to go to 1, right?
What do you mean?
This is going to be like e to the 0.
No?
If the temperature goes to 0, then
Okay, alright.
Right? E is a fixed number. The energy difference is a fixed number. That's just the difference between the two different energy levels. So yes, so for each higher energy boson, the probability gets smaller by a factor of e to the minus e over t. So the probability of finding k higher energy boson is smaller by a factor. You just take another exponent to the k, so you have negative k e over t. So you find that the actual probability of finding k higher energy bosons is this. And basically using Eric's argument earlier, the probability of finding 0 bosons, if you just plug it in, when k equals 0, what happens? The expression just turns into 1 minus e to the negative e over t. And if e to the negative e over t goes to 0, then p of 0 basically equals 1. Or very, very close to 1. Which means you basically have almost 100% chance of finding your particle in the lowest energy state, and basically 0 chance of finding your particle in the higher energy state, which is E2, when the temperature is really low. Which makes sense. When the temperature is low, everything is basically sitting there, and they're not getting excited to higher energy states. So in this case, we really only analyze the system for where the system has 2 different energy states. In general, the system can have many, right? As we saw earlier in Lydia's example, in an orbiting case, we would have many different energy levels depending on which shell you're in. So in that general case, we'll define the lowest energy state to be the ground state, which is 0, and then all the higher energy states can be indexed by number n. So notice that the energy is not really proportional to the number inside it. This is just a way of indexing it. So it turns out that if you do a more general calculation, that below a certain critical temperature, a lot of bosons will suddenly congregate and stay in the ground state. As we saw earlier, the lowest energy state is the ground state. So basically all of the bosons will be in the ground state. That's a very strange type of phenomenon, and that never happens in regular temperature and without the help of quantum mechanics. So in some ways, once all of the bosons we use the word condense. They condense into the ground state. You cannot distinguish between them. Say if I have 10 different bosons, they're all in the ground state and all congregated in a small region. You cannot distinguish, cannot have individual properties of each of them. So they sort of behave as a bigger structure. So you can have, say, 100 bosons, and they turn into some bigger thing. I don't know what to call it. It's just maybe a congregate boson, or as scientists have a more clever name called the Bose-Einstein Condensate, because Bose and Einstein are the 2 people who derived this kind of new matter. The condensate is just referring to the fact that they all condense to the ground state. So, yes, this is how you can use quantum mechanics to do calculations for identical bosons. So now if you look at your problem set, you can work on section 2, which asks you about some questions about the Bose-Einstein Condensate. We don't have time to, there's another question about superfluidity and superconductivity, which is what this is really used for. But you can think about those and talk to me after lecture, but we don't have time to go over.
Let's kind of talk about some of the interesting things we can derive when we look at bosons closer. Here I'm going to use what we know about fermions and the Pauli Exclusion Principle to look into the physics of how neutron stars exist. Neutron stars, if you might have guessed, are made of neutrons. And neutrons are fermions as matter particles. This means that the Pauli Exclusion Principle, that no neutron in the neutron star can have the same quantum state, applies. And this Pauli Exclusion Principle is what makes a neutron able to happen. Because if we think about our sun is basically in a hydrostatic equilibrium between 2 things: gravity, crushing it in, and fusion reaction in the core, balancing out that gravity. Of course, when you have the fusion reaction of hydrogen, you're burning up this hydrogen, and it's turning to helium, and then you're burning up that helium until finally it gets to a point where it reaches iron. And at iron, fusion no longer becomes kind of an energy efficient reaction. That's a turning point where fission becomes energy efficient. And that's when stars get iron cores, they become red giants and eventually supernova. And what you have left over post-supernova collapse, is determined by how much mass it was in the initial star to begin with. And when you have enough mass, to be precise, exactly greater than 1.44 solar masses, but less than 3, because after greater than 3 solar masses is a black hole, you get a neutron star. So, to talk about we'll have to, we're gonna talk about something called Fermi energy or quantized energy. If we have particles in a box, you can define the particles by some integers. So if you have the box and you have your lattice points, so you have your lattice points at each integer. Each different integer will be a quantized state. And at each point, it'll have an energy corresponding to this equation with the coordinates. Important thing to remember is that each n sub x, n sub y, and n sub z has to be a positive integer greater than or equal to 1. So 0 isn't allowed, negative 1 isn't allowed, 1/2 isn't allowed. Now, if we just treat that whole right term with the coordinates as 1, we can use Pythagorean theorem and make it a radius. So that's pretty simple. Now, with this radius, we're going to use a volume approximation. And more specifically, with the volume approximation, we can say that approximately, if you take 1/8 of a sphere, and does anyone know why we might be taking 1/8 of the sphere rather than a whole sphere in this case? Based on what I told you about the constraints of the domains of x, well, n sub x, n sub y, and n sub z. Well, if you look at it one by one, n sub, yeah, someone say yes to be positive? Oh.
One definitely did.
Huh? Yeah, someone definitely did. Yeah, that's exactly right. It's because they have to be positive. Basically one half of the domain is cut off because n sub x has to be positive. So you have a hemisphere where only n sub x is positive. Then you take another half of that where n sub y has to be positive. And you take another half of that where n sub z has to be positive, and you get a 1/8 sphere that describes the positive octile of the three-dimensional coordinate system. And this is a good enough approximation for the number of energy states. We have to multiply this by 2. And we're going to say the maximum number allowable energy states is when there's a neutron in every energy state in this given volumic sphere. So we can get the total number of states by taking this volume and multiplying by 2. The 2 is because in a given state you have 2 because of the spin, which you have to take into account. So you have E sub r as a function of the radius. Now, important to keep in mind is this is an approximation, not only because we're using volume of the sphere to approximate states, but because these energy levels are quantized, and we're basically just adding up energies at each shell. So this isn't exact, but for our purposes, it's good enough, and we're going to get an answer that's pretty close to what we want. But it's important to remember that these approximations need to be understood, and don't over attribute any truthfulness to what they are.
So what this is this saying, so for a fixed R, you can have different combination of n, x, n, y, n, z, right?
True.
So it's like for a fixed distance on a spherical shell, you can have
Right. So
different coordinates.
So basically what we're doing here is we're saying that at a given radius, you have a spherical shell, right? We're saying that energy, that spherical shell, energy is the same along all that spherical shell. And so we're attributing an energy to a radius, and then that radius has a spiritual cell, and then we're adding up those spiritual cells to get a total energy in this given volume, is what we're doing.
Okay.
And that's this.
So why is that the number inside the volume? Why is that the number of state in the volume?
It's because if you imagine an onion, right? An onion can just be imagined as when you peel the onion, you're taking off one little thin slice of surface area one after another. And what's the surface area of a sphere? It's 4 pi r squared. And so if you want to get
Divided by 8, right? Because you're only taking 1/8 of the sphere, the surface area of that
True.
1/8 of a shell should just
So
be.
we're finding the volume, but we're only finding the positive octile of that volume sphere. So that's how we're finding our n sub r. And then at each n sub r, when we also take account the energy for that given R using E of R. We then can find the total energy given in this volume. So what we find is that the energy in a neutron star is this equation, where m is the mass of a single neutron, v is the volume of the neutron star, and n is the number of neutrons. Now, all these things are constants except for volume. And we can use this volume. Yeah, if we're imagining post supernova collapse, and we have this right now, and it's starting to collapse, right? We have a given certain number of neutrons, and it's starting to collapse. We're trying to find the volume. We're gonna soon set this equal to gravitational pressure, and you'll see how we're solving for volume to do that. So we have everything except the volume. We can use thermodynamics to find volume, to find the pressure given E and V. So, if you took chemistry, remember pistons. What we're using when we do pistons, that E equals negative P delta V, it's basically just F times D, our familiar equation for work, because the pressure is the force over the area, and delta V is the same area. So let's say it's sliding up here. Delta V is this same area times delta H. What this means is that since pressure is total force over total area, you have the two areas canceling out, and you get delta E equals negative force times distance, which is our work equation. And it's negative because if the gas molecules within are exerting positive pressure, if they're putting work upon the piston, they're losing energy. If you're doing work, you're losing energy. So using those things, rearranging so they have negative delta equals that pressure equals negative delta E over delta B, we find that the pressure, the Pauli pressure of a neutron star is described by this equation. And this is positive, so this is an outward pressure. It's exerting a pressure outward from the center of the star. And now that we have the equation for the Pauli pressure with V being our variable, we can then use our equation for the gravitational pressure that's exerted, and we can set them equal to each other. And what we get is that the radius equals c, which is just a constant. That's just variable soup. We were working with a lot of variables, times m to the negative 1/3. Now what we can do is that if the total mass of all the neutrons within the star is 2 solar masses, we obtain a radius of 9.8 kilometers. Now, there's something interesting. Based on this relationship, if you increase the mass, what happens to the radius of the neutron star? Yes, so R equals C times m to the negative 1/3. If you increase the mass, yep, the radius decreases, which is kind of counterintuitive, right? But the more stuff you have, the smaller of a radius of a neutron star is going to happen. So when we compare our 9.8 kilometer answer using this equation, we find that for a neutron star of 2 solar masses, in actuality, it's 10 to 11 kilometers, which is pretty darn close when we think of all the approximations we use, where we used states for volumes, and we did a summation rather than the quantized states that are actually energy states, which is really good. So yeah, higher mass means that you have a smaller radius.
And what's interesting is, so what's on the right-hand side? Do you guys remember what the radius on the right-hand side means?
It's like the radius of
Huh?
That's very vectorized.
So your Schwarzschild radius,
Yeah, that's the Schwarzschild radius. So for a given mass, if the radius becomes that small, then it collapses into a black hole.
and that limit is about 3.5 solar masses. So that's the limit in which neutron degeneracy pressure breaks down and you have a black hole. In fact, the way it goes is that I can't remember where, but leading up to 1.44 solar masses, if it's smaller than 1.44 solar masses, you get actually electron degeneracy pressure. And the electrons are fermions too, so this same principle applies, but it's not as strong. After 1.44 solar masses, between 1.44 and 3, you get neutron degeneracy pressure, and that's how you get the neutron star, which are the densest stars in the universe. But once the mass is big enough so that the radius would be smaller than the Schwarzschild radius, then it all collapses into a black hole. So that's how you can think about neutron stars as the precursors of the lead up to black holes. So yeah, that's how neutron stars work.
Wait, is the sun a neutron star?
No, the sun is just a normal main sequence stars, as we call them, because it's just all that's happening is the gravitational pressure is causing fusion in the core. The hydrogen are just fusing together into helium atoms, and the heat that's given off is just counteracting gravity.
Okay, neither of those have neutrons.
They have neutrons, but it's not tightly dense enough that you can say that neutrons are taking up. What we just did works because what we're assuming is that that in a given volume, a neutron is taking up everything. We're assuming maximum capacity. We're assuming that everything is so tightly scrunched in that there's just no more room left. That's how we're finding this energy. The star doesn't really have gravitational pressure to do that. So it just uses normal fusion reaction. Thank you.
I think the lesson to take away from this last lecture is that quantum mechanics does not just have microscopic effects. It can affect stars, neutron stars, which are astrophysical objects as well. But you see that the effects really come in when things become really dense, when particles are packed very close to each other. And similarly, in the Bose-Einstein condensate, the Bose-Einstein condensate doesn't just randomly form in ordinary temperature, you have to go to extremely low temperature. So in some sense, quantum mechanics, it has macroscopic effects, but it has it under very, very extreme conditions. And in everyday life, quantum mechanics just reduces to classical mechanics. That's why we can just use Newton's laws to calculate pretty much everything. But yeah, so in the lecture notes, if you request them, there will be a more math-heavy derivation of why quantum mechanics reduces to classical mechanics in most everyday cases. We will also see where it starts to break down and where these strange phenomena start to come. So, thank you guys very much. You guys all seem to be the consistent participants.
Yeah, you guys
so
get it.
we're really grateful that you guys came to all of this.
Thanks, Vic.
Everybody.